This is problem 1424 on page 938. A 6 kilogram shell moving with a velocity v naught equals, and they give us velocity in vector format there, explodes at point D into 3 fragments A, B, and C of mass respectively 3 kilogram, 2 kilogram, and 1 kilogram. Knowing that the fragments hit the vertical wall at the points indicated, there's a figure there, determine the speed of each fragment immediately after the explosion. Assume that elevation changes due to gravity may be neglected. Okay, so we're going to neglect external forces essentially, right? And realize that the linear momentum must have been conserved as a whole. Okay. So let's see. The velocity of the shell before explosion would have been 12I minus 9J minus 360K. There's a huge difference. Notice most of the velocity is in the negative Z direction. That makes sense. It was fired essentially toward the wall. If you look at the figure, you'll see what I'm saying. These are all meters per second. So the fragments A, B, and C are, I think, 3, 2, 1. Yeah, 3 kilograms, 2 kilograms, and 1 kilogram. So we're supposed to determine the speed of each fragment immediately after the explosion. Okay. So the A, I'm sure has a vector, the B, and VC. All right, so what do you think we should do? One thing we could do, since we know where the various fragments have landed, is we could figure out the direction of the velocity, right? Immediately after the explosion. I think that would be something worth doing. Let's consider that. So the velocity of particle A, for example, must have been directed along that line from D to A, right? So it's probably a good idea to get the vector R from, and I'm going to try and keep this all together. So I'm going to try and get R from D to A. Okay? And that shouldn't be too difficult. We can write it down just by inspection. So the vector from D to A would look like, let's see, in the I direction, negative 1.5 meters. In the, let's see, where were we? In the J direction, let's see, it looks like that the shell is up at 3 meters. And they don't seem to indicate anything about A. It looks like A is up at 3 meters as well. So I think from D to A, there's 0 change in the y-axis. Does that make sense to you guys, or am I misreading it? I think that's okay. But in the Z direction, there's, of course, a negative 4 meter movement. Let's do the same thing for the other position vectors to get from D to C, or well, D to B, and D to C. Why am I doing this? Well, I'm going to try and get unit vectors from these, which will indicate the directions of the velocities. Okay? So from D to B, there it looks like in the X direction we've gone over 4 meters, so plus 4I, gone up 2 meters, plus 2J, and of course negative 4K by the time we come back to the wall. And then for D to C, it looks like we've got, well, of course we're going to have negative 4K. Let's just write that one down from the beginning. And it looks like we're not going to have any x-axis motion, and we'll drop on the y-axis by, let's see, 3 meters. Okay, so far so good? So how do we get unit vectors out of these. By the way, when you learned statics, I think I used unit vectors U because we're using Hibbeler's book. In this book, he uses lambda for unit vectors, but I'll use U since you're used to it. So you call it U, call it lambda, I don't care, it's the same thing. How do we get a unit vector from D to A? Do you recall?
You have to take the sum of the square root and then you divide by the individual.
Exactly. So what we're going to have to do is take negative 1.5i minus 4k divided by root 1.5 squared plus 4 squared. And of course, notice I didn't bother writing the negative sign because it's just going to cancel. So if you guys wouldn't mind, help me out here. It's good practice for you anyway. What is the square root of 1.5 plus, well, 16? 1.5 squared, I think, is 2.25, so isn't that the square root of 18.25? I think. How much?
4.27.
Okay. And I'm out of space, but does this have any units or no? No, because the numerator and denominator had the same units of meters. So now I have a unit vector pointing from D to A. Let's do the same thing. And by the way, if you're curious, in your book now it's called lambda. So if you see in the book that your author uses lambda, he means a unit vector. Okay. So how about from D to B? Well, we do the same thing. No big deal. Now let's see, 4 squared is 16, 4 squared is 16, that's 32. 2 squared is 4, 32 and 4 are 36. So I can do that one in my head, square root of 36 is 6. So we need 4 over 6, or 2/3 I, plus 2/6, 1/3 J, minus 2/3 K. Everybody see what I did there? I was able to calculate the length of that vector without too much trouble, so I just wrote it down. Similarly here, what's the length of this vector? You should start to recognize 3 squared plus 4 squared square root is 5, isn't it? There's a 3, 4, 5 triangle. So, and let me switch to the author's current terminology. So lambda from D to C, that's just going to be negative 3/5 J minus 4/5 K. Okay, so I've got unit vectors. What do these tell me? These tell me the directionality, right? So the velocity of A after is going to be whatever the magnitude of that velocity is multiplied by lambda dA. Same thing for B and C. I've sort of sidestepped the problem. So far, you knew all of this, or at least it's pretty obvious. What was it that we learned in this chapter that we really applied? What we learned is that the linear momentum before the explosion has to be equal to the linear momentum immediately after explosion. That's what we learned. So how do we write the linear momentum? Well, what is the linear momentum of the original shell? Well, here's the original velocity. If we want the linear momentum, all we have to do is multiply the total mass, and when I say m, I mean the total mass, right? I'll use ma, mb, mc for the masses of the individual particles. But that's the initial momentum. How much is the initial mass? Well, 3 plus 2 plus 1 is 6. So 6 times each of these. So 6 kilograms, oh, I don't want to write all that out. 6 times 12 is what, 70, is that right? No, it's 72. 72 things. 72i minus 6 nines are what, 54? And I need 6 times 360. I don't know what that is off the top of my head. Anybody know?
2160.
How much?
2160.
And the units of this would be kilograms, meters per second. So there's the linear momentum. What do we know about that linear momentum? Well, we know it must be the sum of the linear momentums after impact. So m sub I, v sub I, from, well, I equal 1 to 3, right? So how could we write that? Well, we've got an expression for each of these. And in fact, do you see how we will end up with 3 equations? Because really this is a vector equation with 3 different components. Okay? So there's actually only one way that the momentum can be broken down, because we've only got 3 components. If we had 4, we couldn't solve this problem, in other words. Well, we might be able to. I'd have to think about it a little bit. But basically what I'm saying is, well, really from over there, is that the linear momentum after the explosion must be equal to that which is before the explosion. So this would be what? 72I minus, well, let me just write it this way. L bar equals, and let's expand it out, mass of A times the velocity of A after explosion plus mass of B, velocity of B after explosion plus mass of C, velocity of C after explosion. This should look pretty familiar to you, because when we dealt with impulse momentum, we already did something like this, right? We already talked about, remember the train cars where they were coupled together, and we dealt with them as all 3 together as one body, and then we broke them apart to find the forces in between them. That's similar to what we're doing here. So the linear momentum of the 3, think of it this way, 3 train cars coupled together, and then they become uncoupled, maybe push off of each other a little bit. That's basically what we've got here. So let's see, this would be the mass of A. We need the velocity of A. So let's just write the velocity of A as just the magnitude, just the speed, multiplied by the unit vector for A, which is RdA. So that would be, let's see, let's write it as a vector. So square brackets, which would probably be preferred, minus 1.5 over 4.27I minus 4 over 4.27J. Was it J or K? Yes, J. Doesn't look much like before. So that's this first term, plus the mass of B multiplied by the velocity of B. Well, let's again use the magnitude, velocity of B, multiplied by 2/3 I plus 1/3 J minus 2/3 K. Help me out with the last term. What should I write for the last term? I need to take care of that one.
I think it's 3/5 J minus.
So mass of C
times
times
the velocity of C
velocity of C times.
times the unit vector, which is negative 3/5 J minus 4/5 K.
Excellent. So not very difficult. This is not difficult for us to do. Notice that this is equal to L bar, the initial linear momentum, which we know, 72I minus 54J minus 2160K, if I can fit it in there. What do you see? I see 3 equations, 3 unknowns, because look, we can pick off the I components, pick off the J components, and pick off the K components. So how would those equations come out? Well, we'd have 72I equals MAVA times negative 1.5 over 4.27. That's this term. Is there an I contribution here? Yes. Plus mass of A, mass of B, excuse me. This is a B, not an A. Mass of B, velocity of B times 2/3 I. There's the first equation. Oh, I forgot the I here, didn't I? And of course the I's all cancel. And there's our X component equation. In the same way, we could write negative 54J equals mass of A, velocity of A, times negative 4 over 4.27J. B has a contribution, so plus mass of B, velocity of B, times 1/3 J. And then the last term, plus the mass of C, velocity of C, times negative 3/5 J. I don't care if the J's inside or outside of the parentheses, doesn't make any difference, it's just gonna cancel. So now we have 2 equations and 3 unknowns. Help me write the final equation, how would it go?
Negative 2160 K.
You're right. Equals?
Mass of B, velocity of B.
Notice there's no K for A, so yes, mass of B, velocity of B.
Negative 2/3 K.
Good.
Plus mass of C, velocity C, negative 4/5 K.
And of course, cancel the K. Now we have 3 equations and 3 unknowns. Okay. So now we have to solve these in order to get the velocities, or at least the magnitudes. So, let me do this. Let's see, we don't need this anymore. We also don't really need these, because all we really need are the unit vectors in order to indicate the directions of the velocities. In fact, wait a second, we've already incorporated these, haven't we? We don't even need those anymore. I do want to leave up the initial linear momentum and the masses of the various particles. Let's see, I don't think you care about that either. So, let's see, where shall we begin? We've got mass of B here, mass of B there, mass of A and C. Any way to add these and make our lives easy? I should have, let me do something. I should have, let me move this over. Mass of C, velocity of C, negative 4/5. I'm going to move that. All I need to do is remember negative 4/5. Mass of C, velocity of C, negative 4/5. And then I want to move the mass of B, velocity of B 2/3, well, negative 2/3. There. And we'll just get rid of the unit vectors in all the equations because we don't need them anymore. It'll make it look a little easier. The reason I did this is I wanted to put like terms together so I could see if there was a way to multiply and add in order to get rid of things quickly. But I'm afraid I will have to, let's see. Tell you what, let's number these. Equation 1, equation 2, and equation 3. Now it's just solving 3 equations and 3 unknowns. So let's do that. In fact, we don't need this one either, do we? So if I make a mistake, I just really mess myself up, but hopefully I haven't made a mistake to this point. All right, so what I'm going to do in order to eliminate this term is I'm going to multiply equation 1 by 4 over 1.5. And I'm going to add to it equation 2. You see what I'm doing? So if I multiply equation 1 by 4/5, then this term will become, no, not 4/5, 4 over 1.5. Then that'll get rid of this 1.5 and I'll have negative, well, actually I guess I'll have to subtract. Okay, so I'll have negative 4 over 4.27, but if I subtract equation 2, then that will add this term and those two will cancel. You see that? I'm just trying to get rid of that to start. So let's see, if I put those two together in that way, what will I get? Let's do it this way. So I'll take equation 1, multiply it by 4/5. So I will need 72 times 4 over, I keep saying fifths, I'm sorry, I mean 4 over 1.5. Maybe I should say it as 8/3, how's that? Equals, this term will go away because I'm going to add it to -2, so I don't have to worry about that. So 8/3 of MBVB times 2/3. Okay. That's all that will be left from equation 1, because once I subtract off equation 2, then the like terms will disappear. So if I subtract this off, what I'll have, let me just insert it in here. I'm subtracting negative 54, so I'm adding 54, right? And then on this side, this term will be gone, because it canceled. That was my whole reason in multiplying by 4 over 1.5. But then these terms just have to be added. So But wait a second, I'm subtracting, so minus MB VB times 1/3, and then negative times negative is positive, so let me say plus MC VC 3/5. Okay? Now let's try and make our lives a little bit easier. Let's rewrite this. Let me put it up here. So 72 times 8/3, just so I can keep myself straight, plus 54 equals, and let's see, if we put these two together, well, we'd have 8/3 times 2/3, that's these two, minus 1/3 from this term, times MB VB. If I make a mistake along the way, please catch me on it, okay?
Where did the 8/3 times 2/3 come from?
8/3, well, 4 over 1.5 is the same thing as 8 over 3, isn't it?
Okay, yeah, gotcha.
Times 2/3 is this term over here, so I just put them together. Plus, let me move the factor out front, 3/5 MC VC. Okay, so that's, I've taken equations 1 and 2 and put them together. And now I have two equations and two unknowns, because equation 3 involves VB, VC, just as does the combination of equation 1 and 2. So if we look at it, is there an easy thing we can get rid of? I think we should try to get rid of MC, VC, because it'll be easy to figure out the factor for it. What factor should I multiply equation 3 by in order to add it to this one? My goal is to get rid of this last term.
3/4.
I should multiply this by 3/4. Everybody see that? So I'm going to take equation 3, multiply it by 3/4 and write it right here. Okay? So 3/4, well, that's negative 2160 times 3/4 equals, I need 3/4 here. This is a negative sign. I'm going to pull it out. And here's something that most students would try to do. They try to figure out what the result is from 3/4 and 2/3, which you could do, but why bother? Why use your brain power doing that? Why not just let the paper do the work? So I'm just going to write negative 2/3 multiplied by 3/4, and I'll continue to simplify later, MB VB. And then over here, let's see, negative, so I'll pull it out front, 4/5 times 3/4 MC VC. Now I can easily just cancel the 4. The 3's cancel nicely. And I'm going to add these together, right? But before I add them together, maybe I should simplify things a little further. Maybe I should note that this is the same thing as negative 1/2. And that's just negative 3/5. Okay? So if we add these two together, then what will happen is these two will cancel, because this one's positive, that one's negative, so those are gone. And so now we have 72 times 8/3 plus 54 minus 3/4 of 2160, that's all the left-hand side added together, equals 8/3 times, well, we could simplify a bit, I guess, I just don't want to yet. Well, no, maybe I do. 16/9, well, minus 1/3. MB VB, but we have to add this in. This is just a half, so also minus a half. MB VB. Of course, MB is just 2. And what units will VB come out in? I've been consistent so far using meters per second, so it should just be meters per second. So the velocity of B immediately after the explosion, its magnitude at least, should be 8/3 of 72 plus 54 minus 3/4 of 2160, that's the whole left-hand side, divided by 2, that's the mass, times 16/9 minus 1/3 minus 1/2. There's the velocity of B. Okay. If you don't mind, tell me what velocity that comes out to. I know it's a little bit of a mess. There it is. Maybe easiest to calculate the denominator first.
The numerator is negative 1374.
Numerator's 1374.
There you go.
Okay. What about the denominator? It's gonna be some irrational number, I imagine. So go to 1/3 in there. We could say this is 3/9. If we did that, we'd take 3 away from there. That might not be a bad idea.
I
I
think everything is negative 727.4.
Negative 727.
That's what the whole last answer is. I didn't calculate the bottom. That's what the final answer is.
For the velocity of B,
Yeah, negative
Yeah.
727.4.
it should not come out negative. We should have a positive number, because I wrote the vector, the unit vector from, D to B. And you know the velocity's gotta be along that line, so we may have made a mistake somewhere. So you're saying, yeah, this would be a positive denominator, wouldn't it?
Did we subtract equation 3? Or did we add it?
We were trying to add them together because this one was already negative, that way we got rid of those two. So we should get a positive VB, and unfortunately I've erased so much, I don't know where we're wrong. Basically, we need to solve these 3 equations and 3 unknowns. At least the 3 equations are still there. And I assume you guys have not had anything to do with linear algebra where you set it up as a matrix and invert the matrix. But I think once we solve these equations, we should end up with VA, VB, and VC. So I'm sorry I haven't to solve them ahead of time. But I must have made a sign error somewhere, because we should get a positive number. Okay. So we should get a positive number for both VA, VB, and VC that solves these. What I might do is, off camera, I'll just solve them while we take a break and tell you what the numbers are. But if I haven't made a mistake up to this point, then we could calculate VA, VB, VC, and then we could write them as vectors, right? Because that would be ideal. We could take the unit vectors, multiply them by the magnitudes of VA, VB, VC, and then answer the question of what is the velocity immediately after the explosion. Does that make sense to everybody? It's not a difficult thing. The only thing that makes this hard is this solution at the end. And that's the only thing that makes it a little confusing. Yes?
Is there a way that whenever we have time, we can solve it closer than it's supposed to be, so that we can make sure we don't write it?
Oh, sure.
So I stopped somewhere along the way, I was like, I feel like this needs to be a term. So I stopped and I was like, indicator.
Sure. Yeah. Okay. Anything else? All right. Okay, guys, let's continue with the example problem. I figured out what I did wrong. It's right here. Notice that for, this column here would all be for particle A, this column's all for B, and that's all for C. It makes sense that all 3 particles had to move in the negative Z direction. Does that make sense? So why did I put negative 4 over 4.27 here in the Y equation? It should be down here in the Z equation. So that's what's wrong. I should have moved this down here. Mass of A, velocity of A, negative 4 over 4.27. So that was in the wrong place. I just copied it wrong. Notice all of these are negative 4. Well, that one's negative 4 over 6, right? I just simplified it down to negative 2 or 3. So that's where I went off. And so once I put that into the correct place, then I used an online equation solver to solve 3 equations and 3 unknowns so I didn't mess up the algebra. Here's the numbers I got. For the velocity of A, at least the magnitude of the velocity of A, I got 140,056 over 325. For the velocity of B, I got 5130 over 13. And for the velocity of C, so all of this would be junk, by the way, because the solution strategy was not going to work since I had determined the wrong place. So for C, I got 6870 over 13. So there are the magnitudes of the velocities, and if I still had the unit vectors, we could figure out what these magnitudes really are, multiply them by the unit vector, and write down the velocities as vectors, okay? But we knew we should have positive numbers from these, and now we have, so I'm more certain that my solution is correct. I verified the other terms as well, and they are in their correct place now. Any questions about this problem? All right.